Hello, calculus students. This is Mr. Bean. Here we go with another lesson. We're now into an entire new unit. We're going to talk about the derivative in this unit, but before we do that, this first lesson, we won't really talk much at all about what a derivative is, so you're just going to have to hold on for that until the next lesson. Today we're focusing in on this thing called average rate of change. I'm hoping this is going to be really easy for you and that we can kind of baby step our way into the derivative. So average rate of change, let's remember what in the world that is. If you recall rate of change, that is basically the same thing as just slope. I mean, really, this is like our pre-algebra days where we'd have slope and you'd take the two different y values, subtract them, and blah, but you remember this stuff. Okay, and then or another way of writing this, a fancy way, is to use delta y, delta x. That just means the change in y, the change in x. And that is also, if we wanted to get in a little bit more deeper conceptual understanding, we're going to say it's the dependent unit per every independent unit. Probably the easiest way for me to think of this is if you say miles per hour. That's one of the most common ways of thinking about this. Miles per hour. Miles would be the y-axis or the dependent unit, and then the independent unit would be the hours, which is on the x-axis. That's why it's the y values divided by the x values for all of these other things. Okay, so that's rate of change, stuff you've been doing for years now. So hopefully this will make sense as we start getting into a little bit of calculus with this. So the fancy way of writing this out, you should already have this down in your notes, so you don't have to write too much of this. That is, you've got a continuous function, and it's going to go on the interval a to b. So these are x values. We're going to start at a and go to b. So what do we do with that? You take the y value minus the y value, and on bottom you have the x value minus the x value. But look how I have or here, because it does not matter which one you start with. You know, if I go back to this and how it says y2 minus y1, y2 does not mean the second y. It just means it's a different y than this one. So it doesn't matter which one you start with. You just have to figure out what the y values are, and then on bottom you do it in the same order, subtracting the x's. Now this is a part that you may not understand what I'm talking about, and that is when you get this slope, the average rate of change between 2 points. In fact, you might even put that down out here on the side of your notes. That average rate of change just means the slope between 2 points. The slope between 2 points. That's all the average rate of change is. So this key word here, the secant line, it's the slope of the secant line. Now you may not know what the secant line is. Some of you will have discussed it in geometry, but I've found a lot of calculus students don't remember or have any idea what that word is. So let me show you what I'm talking about here. We're going to do our first example. I do have there's a calculator on this one, so you might grab your calculator just to make sure you can do this as well. It's not necessary to pull it out. You can just watch what I'm doing. We're going to find the average rate of change of this function on the interval 1/2 to 3/2. In order to find the average rate of change, we need to figure out what the y values are for this thing. So we're going to plug in a 1/2 and a 3/2 and see what that equals. Okay, so I could do this longhand. I'm going to cheat my way around this one and use the calculator to get this a little bit faster. And so that is going to give me, if you pull up the calculator, what you'll do is you'll plug in y1 equals this thing, 3x squared minus 2x. So we plug that in here. Or I said 3x squared, I meant, x cubed minus 2x. So we're going to plug that thing into y1. And now this is what we get. You get this graph. What I want you to do on your graph there is to plot this point right here. What I did is I did trace, and then I plugged in 0.5 for the 1/2, and it jumped to this point on the graph. So go ahead on yours. Let's just put a fill in that dot right there, and it represents, you can go ahead and write that down on your notes as well, that f of 1/2 is equal to negative 0.875. Now that is a nice fraction. We could figure that one out, but we're speeding this up here. Okay, the next one, we're going to figure out what f of 3/2 is. So f of 3/2, I'm going to hit trace, hit enter, it jumps to 1.5, and it's going to equal 0.375. I forget what that fraction is. So there we go. Now go ahead and fill in the dot there. Now the secant line is the line that just connects those 2 points, this. So go ahead and sketch that graph and label it. That right there is the secant line. That's what this is. Okay, so when we get the average rate of change between any 2 points on a graph, in this case this point and this point along that interval from 1/2 to 3/2, and you connect them, it's the secant line, and the slope, the rise over run, is the slope of the secant line. Okay, example number 2. We have this function, blah, blah, blah. I always say blah, blah because, it doesn't really matter what this function is. We just have a function. We're going to come back to it. I don't even need to understand the function yet. It's how long it takes Mr. Brust to clean his house, where H is measured in hours and K is measured in the number of kids Mr. Brust has. They keep multiplying at his house. So we have here this, I like this example, one, because it's a joke to think Mr. Brust is going to be cleaning his house. But the other part of it is that hours is not always the independent. Time's not always along the x-axis. We're used to thinking that this is always time, but this is an example in where that is not the case. So it is going to be that the hours are along the up and down y-axis. Let me get rid of this. So what is the average rate it takes to clean his house if he has between 1 and 4 kids? So that's basically saying that my interval is going from 1 to 4. That's my interval. So this is like my A and this is my B. So we've got to figure out what the y values are at h of 1. And we need to figure out what the y values are at h of 4. So pretty simple here. You just plug it in. You get 3 times 1 squared minus 1. That's just 3 minus 1 is 2. And then if you have 4 kids, so this is 2 hours. If you have 4 kids, it's going to be 3 times 4 squared is 16. Minus a 4, that's going to equal 16, 32, 48, 48 minus 4, 44 hours. Did I do that right? Yeah, okay, phew. All right, so then what's going on here? The average rate of change is going to be the y value. So let's go 44 minus 2 over, and since I started with the 44, I got to start with the 4 on bottom. 4 minus 1, that's going to equal 44 minus 2 is 42 over 3. And does that go in evenly? I believe it does. And that is 14. So the important thing here is when we're talking about an actual word problem that has an application to it, you must have units. It's very important in calculus that we always include our units if at all possible, if they represent something. And so in this case, it is the y value is the hours and the x value is the kids. I shouldn't say y and x because we're using h and k, but I should say dependent and independent. So this is going to be that it takes him 14 hours per kid to clean his house. It takes 14 hours per kid on average. Okay, moving right along, let's go to our next example. Now we've got this really weird thing. Find the average rate of change for this thing on the interval x to x plus h. What? X to x plus h. There's no numbers here. How are we supposed to get an average rate of change on an interval with no numbers? So this is something that we're going to do today in this lesson in order to help you prepare for 2.2. If you can get this down pretty well, it's really going to help you when we get into the definition of the derivative. So this is going to be some good practice today. So let me show you what I'm talking about. On this same web page, I should have something that looks like this. So this is, I made this in something called GeoGebra. Whoa, make that smaller. GeoGebra. I don't remember how to say it. So, and I made this on, it should be on your website as well. So you can be able to kind of play with this yourself if you want. So what I'm going to look at is if I have any point, so this is just like your example, x squared minus 4x plus 1. You can see that here. I've got any point x comma f of x. Okay, I can put it wherever I want. It doesn't really matter. Let's just put it right there. Boop. So if then I have a second point, and I can be anywhere I want, this other point. This other point, I'm going to call it x plus h comma f of x plus h. What does this x plus h means? It just means that it's h more units away from x. Again, I don't know what h is, but it's right here. So if this x value is x, I'm going to go h more, I'm going to add h on, and then this is my x plus h, x value. Well, if I want to know what the y value is, I've got to plug in an x plus h into this function. So in this one, I just plug in an x, and in this, to get this blue dot, I plug in an x plus h. Okay, so this is the visual representation, and again, you could have it over here, you could have it here. This is just kind of, you can kind of play around with this if you want and see. This also gives me the secant line. You can see in red I've got the secant line, and up here it's giving me the slope of that secant line as it's going through. So let's use these variables. Let's go back to this problem here and try this out. So this is what I'm talking about when we're doing this. In order to get this rate of change, I'm going to come down here and I'll have you think about this part. I'm going to plug in an x plus h into the function. Then I'm going to subtract just an x plugged into the function. Let me repeat that. Remember how we're going from this x value to this x plus h value? So let's figure out the y value with an x plus h in, and then subtract just an x plugged in. On bottom, here's the x value, x plus h. You're going to subtract the original x value. This whole thing simplifies because you have this x minus x to this. So this is really what we're doing here. We're going to plug in an x plus h and subtract f of x, and then all over h. Okay, here we go. Let's try it. So we have, plugging in the x plus h first, we're going to plug it into this x and into this x. So you'll have x plus h quantity squared minus 4 times x plus h plus 1. So what I just did is I plugged the x plus h into this x and into this x. You have to put them both into both of them. And then we're going to subtract f of x with an x plugged in. So now we're just plugging in an x, plugging in an x. Well, it just means it's the same thing. But you have to put parentheses here because remember we're subtracting the entire f of x. So minus 4x plus 1. Okay, so in blue here I'll underline this. This right here represents f of x. We subtracted the entire thing. If you look at this formula right here, we're subtracting f of x. Okay. Now we also have to have a fraction, so make a fraction here, and this is all over. You need to write smaller than me, by the way, because I got more space on mine, so you need to write a little smaller. So this is going to be the x value was x plus h minus the other x value was just an x. Okay, let's start cleaning this thing up. So x plus h squared, what is that? Remember, this is like x plus h times x plus h. That's what this thing is. So hopefully you know how to multiply this out, distribute, FOIL, however you want to call it. So this is going to become x squared plus 2hx plus h squared. I'm skipping the step of multiplying that. And then we're going to distribute the 4. So minus 4x minus 4h plus 1 minus x squared plus 4x minus 1. I took this negative, distribute, all over. Oh man, that's hard to write. Do that straight. And then the x minus x cancel, so you have all over h. All right, let's clean this up a little bit now. What can we cancel? I see an x squared here and a minus x squared here, so that's going to cancel. And then I have, let's see, a minus 4x here is going to cancel with a plus 4x here. So those are gone. I have a plus 1, which is going to cancel with this minus 1. So those are gone. So all I have left is a 2hx plus h squared minus 4h all over h. If you do this right, you're going to have a bunch of h's here that you could factor out. So I'm going to say that this is now equal to factor out an h, and you're left with 2x plus h minus 4 all over h. Cancel, cancel, final answer, 2x plus h minus 4. So what in the world does this give you? This gives you an equation that represents the secant line, the slope I should say, the slope of the secant line. I need to erase that and write that correctly. There we go, slope of the secant line. That's what this is representing. So if you knew what the x value, let me go back to my GeoGebra cool thing here. If we knew what, let me move this aside. If we knew what the what this x value was, in fact, let's just do it right here. So if I have an x value of 1, and let's find another coordinate point that crosses on here. Up here at 6. Okay. So if I have an x value of 1, and my h is 1, 2, 3, 4, 5, then you can plug a 1 in here and a 5 in here. And let's see what the slope is. Let's try that, just for fun here. We said the first x value, no, what did I say? I'm confusing myself. The x value is a 0. 0, the h is a 5. Sorry. I messed up there. There we go, that's better. Sorry for that confusion. So we said the x is a 0 and that the h is going to be a 5. So what does that give us? 2 times 0 is 0. 5 minus 4 is 1. So that would mean that the slope of the secant line is 1. Let's see if that worked. So you look back up here. Here's the slope of the secant line. Well, I've got 1.02. That's only because my dots are off a little bit. So if I had it exactly on that coordinate point and exactly on this coordinate point, then it would work out to be 1. So again, that when you plug in an x plus h and an x, it gives you a formula, an equation here, a little expression that gives you the slope of the secant line if you know what the x value is and you know what the h is. Now that might not seem like that big a deal. Like, why in the world would you ever do something so complicated? Because we're going to do that in the next lesson, but we're going to throw in some limits. It's going to be so exciting, and we're going to make h become 0. It makes no sense yet, and it's going to go to something like that. It's okay. We'll talk about it next lesson. Don't worry about it. So that's it for now for this stuff. Hopefully that was simple enough. This would probably be the most confusing part, I'm guessing. Let's rock that mastery check, and I'll see you back in the next lesson where we're going to do the definition of the derivative.